Charles's law depicts the relationship between the volume and the temperature of a gas. And what we see from the graph on the right hand side is that there is a direct relationship between the volume and temperature of a gas. Now this is assuming that we keep pressure constant. So what does it mean to have a direct relationship? Well, this means as one variable goes up, so does the other one. So here we see that if the temperature increases, the volume of the gas must also increase if we're trying to keep the pressure constant. Whenever you're solving Charles's law problems, you need to make sure that you always change your temperature to Kelvin. A lot of times our experimental measurements will be made in Celsius, but then we simply add 273 and that will be in Kelvin. So always do your calculations in Kelvin. If a problem asks you to change your answer back to Celsius, then we can do that, but let's go ahead and always do those calculations in Kelvin, and then in the end we can change it back to Celsius. So between these two variables, between volume and temperature, we're looking at a direct relationship. So what we're going to see here is that we can derive an algebraic expression that relates these two variables at different conditions, and that equation will be V1 over T1 must equal V2 over T2. So let's see if we can solve a problem relative to volume and temperature using Charles's law. What we have is a gas that is occupying a volume of 200 milliliters, and we're going to expand that volume to 400 milliliters, and we'd like to know how is that going to affect the temperature. Our temperature here is starting off at 100 degrees Celsius. You may recall that we always want to do our calculations in Kelvin. So we're going to go ahead and add 273 to the 100 so that we'll have our temperature in Kelvin, which is the 373. Now we notice that our volume is increasing, so our temperature must also increase. Here our volume is going up by a factor of 2, so our temperature is going to have to go up by a factor of 2. To solve for what that final temperature is, we can use our algebraic expression V1 over T1 must equal V2 over T2. If you cross multiply here and algebraically solve for the unknown variable, solve for T2, you'll find out that you have a Kelvin temperature of 746. Since we want our final answer here in Celsius, now we can go ahead and subtract the 273. And our final answer here, based on doubling our volume, going from 200 to 400 milliliters, made our temperature go from 100 degrees Celsius up to 473 degrees Celsius. So what you see in front of you is the algebraic method of solving a Charles's law problem. We can also use the fractional method, so let's take a look at that. Here we're simply recognizing that if the volume is increasing, the temperature has got to go up as well. So if we multiply our initial Kelvin temperature by a volume fraction, that's going to actually make that temperature go up, and there's two ways to set up that volume fraction, either 200 over 400 or 400 over 200. And since there's a direct relationship between these two variables, we want to set up the fraction so that it's greater than 1. We need our temperature to go up here. So if our volume's going up, our temperature's got to go up, we got to set up this fraction so that we get a number greater than 1. So our volumes here, 400 over 200, will give us a volume greater than 1. So if we multiply our Kelvin temperature, the 373, by our volume fraction, then we will get our new temperature of 746 Kelvin. And then subtracting the 273, our final answer here in Celsius based on our volume, going from 200 milliliters up to 400 milliliters, would be the 473 degrees Celsius.